All right, let's tackle a question today that on the surface sounds kind of ridiculous, but trust me, it gets to the absolute core of what we think we know about math. The question is, do numbers even exist? Let's get into it. We all have this really comfortable relationship with numbers, right? They're predictable, they're solid, they're basically the foundation of how we make sense of the world. 1 plus 1 will always be 2. But what if that foundation isn't nearly as solid as we've been led to believe? What if the whole idea of an infinite string of numbers is actually, well, built on a fantasy? So, to really get to the bottom of this, we have to start with a concept we all kind of think we understand: infinity. But the source material we're looking at today throws down a pretty serious challenge right out of the gate. Wow. I mean, that is a bold claim. It's saying that two of the most fundamental ideas in all of mathematics, the very things that our entire system of calculus is built on, don't really have a proper, solid definition. And get this isn't some obscure secret. The source argues that it's a known issue, one that's just kind of ignored in school and university. You're told, oh, it'll be clarified later, but it never is. And the whole problem really starts with how we think about counting forever. Okay, so this distinction is absolutely crucial. On the one hand, you have indefinitely. That just means a process that can keep going, like you and I counting. But it's a real process, and eventually it has to stop. On the other hand, you have infinitely. This suggests the process is somehow already finished, like a complete endless list of all the numbers just exists somewhere. The source says this is just impossible, and this is what leads us to the real troublemakers. So this brings us to this idea of big numbers, and honestly, this is where the argument gets really fascinating. Now that is a wild statement. And we're not talking about a billion or a trillion here. We're talking about numbers that are so unbelievably vast, so different from what we use day to day, that they basically just break the rules of being a number. Here's the problem, right? Think about it. If a number is so huge that you can't possibly write it down, how can you even be sure what it is? How do you tell it apart from the number right next to it? And if you can't even specify the number, how in the world are you supposed to do something as simple as add 1 to it? At a certain point, you have to ask, is that even a number at all? I just love this quote because it makes the problem feel so physical and real. It's not just some abstract philosophical puzzle anymore. It's a genuine, practical, physical limitation. And here's why. The source points out that there are fewer than 10 to the power of 100 particles in the entire known universe. Just think about that. It means that for the overwhelming majority of so-called numbers, we literally don't have enough matter in the universe to write them down or store them in a computer. They are physically impossible to even express. Okay, so if these big numbers don't really exist in any practical way, what does that do to the formal textbook definitions we all learn? Well, it pretty much breaks them. So here's the standard definition you'd find in a math book. Seems pretty straightforward, right? A set is infinite if it's not finite. And a set is finite if you can count all its stuff and stop at some number n. Simple enough. It seems perfectly logical, but our source argues there's a killer flaw hiding in plain sight. Do you see it? It all comes down to that one little phrase, for some n. The entire idea of finite, and therefore infinite, is balanced on our ability to match a set to the numbers up to this n. And boom! There it is. That's the punchline. The definition completely trusts that some n will always be a nice, well-behaved, identifiable number. But we just saw that almost any n you could possibly pick is one of those big numbers that we can't write down, can't identify, and can't really work with. The whole logic just collapses. If the n you need to prove a set is finite might be an unknowable big number, then you can never be 100% sure that any given set is actually finite. And if you can't be sure it's finite, the definition means you can't be sure it's infinite either. The definition just fails. And this all leads to a really profound and honestly kind of unsettling conclusion about what math itself really is. Think about this for a second. We tend to believe that the answer 21 exists out there in some perfect, abstract world of ideas, just waiting for us to see it. But the source argues, nope. Without a mind or a computer to actually do the calculation,
that string of symbols is just meaningless ink on a page. It doesn't produce anything on its own.
And this leads to the final major point. Math isn't some disembodied truth floating around in the cosmos. It's a process. It's something you do, and it requires a physical host to run on. Our brains, a computer, even just pen and paper. It has to exist in physical reality.
And this is the ultimate challenge posed by the source. It's a demand for actual physical proof. If you're going to claim a number exists, especially one of these big numbers, you ought to be able to produce it. Show it to me. But for almost all of them, you just can't.
And that's really the question to chew on. If numbers and math aren't a feature of the universe that we just discover, but are more like a tool we invented, a piece of software that needs our hardware to run, how does that change the way we see the world? It's a huge shift in perspective, and it suggests that the universe of numbers might be much, much smaller than we ever imagined.